Hi, welcome to Concept Base. I'm John Hepworth. This one is for Year 11 Extension students. We are in the Polynomials section of your scope and sequence, and we're looking at remainder and factor theorems. Now, there's two options in your extension class. You're either doing advanced extension combined, which means you're probably not up to this bit, or you have an extension class which is separate with a different teacher to your advanced class, which means you're probably in these polynomials. Either way, you will be covering this content. If you're in that sort of combined advanced extension class, then this will probably come in a few weeks' time. But let's have a look at what's going on here. And hey, it doesn't hurt to get a little bit of content before you get taught it in the classroom, because you get a bit more understanding of those ideas before they're presented. Okay, so here we have divide a polynomial x cubed minus 2x squared plus 3 by another polynomial, x minus 1, and then express the original polynomial in a form p of x equals a of x times q of x plus r of x. What is going on? Okay, this is completely new. We haven't really done specific polynomial division in year 10 at all. We've certainly factored polynomials, but we haven't gone and divided them specifically. We've dealt with algebraic fractions, but nothing with this sort of explicit polynomial division method. So let's have a look at what polynomial division is. To do so, first of all, what we want to do is just do a little bit of revision of what division is. Now, for an extension math student, you might think, I know what division is, but let me just express it in a particular way. Say we had the number 13 and we wanted to divide it by 4. What would we do? We would say, how many 4s go into 13? Well, 3 of them do. If we then do 3 lots of 4, we then have 12. So far we've gotten up to 12 in terms of our dividing into this 13. If we took that away, 13 minus 12, it would leave us with a remainder of 1. And we would seek to see whether or not we could divide it by 4, and we can't, which gives us an option. We can then write it as a remainder of a quarter, 3 plus 1/4, and therefore we can say that 13 divided by 4 can be expressed as 3 1/4. Or we could express this in another way, which I'll show you as well when we look at the algebraic setup. Well, actually, let's go here, and we could just add this remainder of 1. How could we do that? Well, we could actually multiply both sides by 4 here. If we multiplied both sides by 4, we could say 13 equals 3 times 4 plus 1. Okay, so that's a little bit of a strange way to write it. 3 times 4. How did I come up with that when I times this by 4 just here? So a way of writing 3 1/4 is 3 plus 1/4. And so if I times 3 plus 1/4 by 4, well, that's 3 times 4 plus 1. And so now I've got my number 13 written in a very specific form. I've got it written as the original number, and then I've got it written with a divisor. So I might just write these around the other way just for the format of what we've got above. So I've got my number, and then I've got my divisor, and then I've got my resultant quotient, and then I've got my resultant remainder. So I've now written this number, which obviously we are going to work out as being a polynomial, in a very specific form that expresses it as a divisor times its quotient plus a remainder is giving this number 13. 4 times 3 plus 1 equals 13. And so we're being asked to do that. But we're being asked to do that with this polynomial. So to do that, we are actually going to follow this exact process identically as we did in the numbers, but we're going to do it with the polynomial expression. So let me just get rid of this. Now, sometimes these types of questions can take a lot of working out, and they can be really tricky to make sure that you don't make any basic errors with minusing a minus and so forth. But let's have a look at what it looks like. So we are dividing x minus 1 into x cubed minus 2x squared plus 3. So we're going to do exactly what we did before by putting 4 into 13. We're going to say, well, how many times does this x minus 1 go into this function? And what we want to look at is we want to look at the first term in both of these polynomials, and just divide those first, and then let whatever happens after them be dealt with later. So I'm going to go and divide x cubed by x. So how many times does x go into x cubed? It goes in x squared times. Now you may recall with the 13 one, I then multiplied the top by the divisor and wrote it underneath the number. I'm going to do the same again here with this polynomial. So x squared times x is x cubed, and then x squared times -1 is negative x squared. So now what I'm saying is, I'm saying x minus 1 went in x squared times. So I'm taking x squared lots of x minus 1 away from the polynomial because I've already divided that in. And I'm then going to deal with what I've got left. So x cubed minus x cubed, gone. Negative x cubed divided by, minus negative x squared is just going to give us 1 negative x squared. And 3 minus nothing is 3. We then go and divide it again. How many times does x go into negative x squared? Well, it goes in negative x times. So now negative x times x is negative x squared, but we also have to times the minus 1. So negative x times minus 1 is positive x. Now, some students won't write this like this. They'll separate that plus 3 away to not get it confused with the x, but I'm just going to go ahead with it here as it is. So now negative x squared minus x squared is 0. So that's gone. And then 0, there's no x squared term, there's no x term in this part of the answer. So I've got nothing minus x, and that's going to give me negative x. And then I've got positive 3 minus nothing, so that's going to give me plus 3. And I'm going to go ahead and divide again. Now I keep dividing while this resultant polynomial has the degree that is greater than or the same as the divisor. In this case, they're both degree 1, so I keep dividing. So x goes into negative x, -1 times. So now -1 times x is negative x, and -1 times -1 is 1. And I go and subtract them away, and I get 0, and 3 minus 1 is 2. And I've achieved the same division by polynomials as I did in that number 13 when I divided by 4. I've expressed it in a divisor, a quotient, and a remainder. So as a result of that, I can write it in the form that it's being asked for in the question, because now I can say that x cubed minus 2x squared plus 3 is the same as x minus 1 times x squared minus x minus 1 plus, now, if I am going to just write plus 2 here, then I just need to be aware in the way in which I've written things. I have not written that this polynomial is divided by something, otherwise this wouldn't be here and this would have been written as a fraction. I'm just writing it as the entire polynomial is equal to the divisor times the quotient plus the remainder. And there is my solution. So algebraic polynomials can be expressed exactly the same way as numbers can be divided, and then we can, and we do it in the exact same process. Divide it by a thing, multiply that back, take it away, see what's left over. Can we divide it further? And we go ahead and do it again. Now, there are a couple of situations where tricks come up in these. You could be dividing by a polynomial that has a higher degree, like x squared. So if you are dividing by x squared, then you would stop when your remainder got down to a polynomial degree 1, because we never want to express our remainder as anything other than a polynomial. And if you started dividing things by degrees that are higher than it, you're going to end up with like a hyperbola term. And in the definition of polynomials, back in the language and definition of polynomials that we did, we said that the x terms are all positive powers, positive degrees. So we never go down to like plus a x to the -1. We don't do that. We're expressing all the x's as positive numbers, or 0. X to the 0 is also available in the polynomials. So we would have stopped if we had an x squared going into a linear term, but in this one we didn't. We just had a linear function, a linear polynomial going into a linear one. So we do keep going because we end up with some constant term, which again is okay. That's a polynomial degree 0, and that's acceptable. That's still part of polynomials that we're doing. So that trick can come up. You've got to know when to stop and consider that that is the remainder of that polynomial. Now, I would recommend that this is one of the types of questions where sometimes doing lots of them is good practice, because the more you do, the faster you get. There is so many opportunities to make errors along the way. As you can see here, we did minus a negative and we ended up with a negative answer. So that can be tricky. Here, we had no x term and we were taking away an x, and we had no constant term that we were taking away from the constant. So that can be tricky as well. Like I was saying, some students line it up differently. They won't write +3 like that. They'll write plus 0x plus 3, so that they've always got the x term there, even though it has no coefficient, just so when they line it up, they don't make an error there. So that's something that you could include in your process if you feel like you're making errors when your polynomials aren't lining up. So we did divide that polynomial. We did express it in that form, ax qx plus rx. And so one thing I want you to note here is this is not in linear factored form. You can see here we have two factors that are multiplying together, but then we've got this constant on the end. So what that tells us is that x minus 1 was not a factor of this polynomial, because if it was a factor, there'd be no remainder. If I would have divided 12 by 4, it would go in 3 times with no remainder, because 4 is a factor of 12. If I divide x cubed minus 2x squared plus 3 by x minus 1 and there was no remainder, then that would also suggest that x minus 1 was a factor. And that's something that you're going to delve into next in remainder and factor theorems is, well, how can we identify that something is a factor, or what remainder it would have if we did divide the polynomial by that polynomial.